Okay, so in this problem, you are given L and R and K. So L and R just means the number you can choose. Let me see. It's actually more like the digit you can pick. And then K is the length of the number. So for example, let's say L equals to 1 and then R equals to 2. That it means that we can pick from 1 and 2. So if R equals 5, it means that we can pick 1, 2, 3, 4, 5, so on and so forth. Let's just stick with R equals 2. So it means that we can pick 1 and 2. And let's also assume K equals to 2. So K is the length of the number, and the digit we can pick is 1 and 2. So therefore, okay, let me just move it here. Therefore, the thing we can pick here is 1, 1, 1, 2, 2, 1, and 2, 2. And the answer that we are looking for is not the count of it, but the sum of it. So 11 plus 12 plus 21 plus 22, it will be 66. This is the total answer they're gonna return. Yeah, that's basically the question. Let's think about how can we solve it. Okay, so how can we solve the problem? Let's think about it in this way. What we can do here is just think about how can we calculate one position. For instance, if we have 0 to k minus position to fill, right? And then if we just look at one position, let's assume that for p in 0 to k minus 1, how can we find the total number of contribution for this position p? The answer is, well, it's still not very straightforward, but it's easier to digest. We know that this is just the current. Let's assume this is current. This is the contribution for position P. Because we know that if we are looking at the 0 position, it will have 10 to the power of 0. If we are looking at position 1, it will be 10 to the power of 1. So the base is always 10 to the power of p. And that's just the base. And then we're going to, well, because of the constraint, we cannot pick any digit. We can only pick L or L plus 1 or ... all the way to R. So because of that, we can just do a plus here, actually. Plus R. This is all the digits we can pick. So we have decided the position and we have decided the digit. Once we have decided both, then we actually also need to think of the mutation for the other position, right? For the other position, it will be the length of that, R minus L plus 1, because this is the number of possible digits that the other position can choose. And what are the other position is k minus 1, because we have k and we are choosing for p. So that's why we have k minus 1 other position to fill, and each one of them will have r minus l plus 1 number of possibilities. So basically we will just do that, and then answer plus equals to cur, and then answer equals 0, and that is like a brute force. Brute force. Okay, that's pretty much the brute force solution. But as we know, k can be really large. K can be about like 10 to the power of 9. So this wouldn't work. But if you look closely, you will notice this is just keep repeating it itself. All right. So let's just assume x equals this one. And what we're going to do here is just, 10 to the power of 0 times x plus 10 to the power of 1 times x plus 10 to the power of k minus 1 times x. So this is basically it. So if we are doing a little bit of math, we can just extract this x, and x times 10 to the power of 0 plus 10 to the power of 1 plus plus 10 to the power of k minus 1. So what is this then? So x we already know. X is this one. We can figure this out in constant time. But what about this one? So this one, if you look closely, this is just, let me copy that. So this is just 1, 1, 1, 1, 1, right? Also known as like 1 repeat k times. So, well, how can we calculate this number? So one dumb way is to we can just loop k times again and plus this, but again, k is really large. We don't want to do that. Another way to do it is we just do 10 to the power of k, which will give us, so 10 to the power of k minus 1 actually. This will give us what? 99999, right? And then basically 9 repeats k times. So once we have that, and this 999 divided by 9 will be 11111, right? It's basically what we want. So that's what we're gonna do. There's some math trick to do the division in modular. So as a result, we don't actually have to like go through k times. That's basically the whole idea for a solution. I feel like I should explain a little bit why this x to the power of p is faster. So if you still remember, what we previously say was we can do something like 10 to the power of k minus 1, and it will give us 99999. Okay, first let me switch here. So this will give us 999, and then we do something like, and then we divide it by 9, and then we get the 1111. So let me move it here. So this actually hinges on how fast we can calculate 10 to the power of k, right? So I didn't explain earlier, but if you do any power, like in general, I'm not just looking for 10 to the power of k, but in general, x to the power of p, I just write it in a function like that. So in this case, let's assume this p is really, really large. The same goes for k. K can be really, really large. We don't want to loop for p times. We want to make it faster. So actually, in this case, we can do like very simple DFS. Here, just assume like, because if p is even, actually I don't know why it's so blurry. Let's say p is even, and then we can just do something like return power x p divided by 2, and then make it like a square. Let me try to resize it. Can I resize it? Yeah. Okay, sure. Okay. So else, it means that it is not an even. Then we can do something like x times power x p minus 1. So as you can tell, we are keep doing this p divided by 2 over and over again. So even if this k is really large, it is very fast for us to reach the base case, which I forgot to mention. The base case is just if p reaches 0 and then return 1, because anything to the power of 0 is just 1. So that's the base case. And even if the p is really large, for us it's really fast to get to 0, because we keep doing this p divided by 2. Of course, sometimes we will do p minus 1, but it's like at most we had the worst case, we do the p to the divided by 2 every other time, because if we are odd now and we do p minus 1, and then p minus 1 is going to be even, because right now is odd, and odd minus 1 will be even. So next time we're going to do the p divided by 2. That's why this can be really efficient. So as a result, this 10 to the power of k will result in log k time. So this is also our time complexity, which I think I didn't mention that before. So the time complexity for the solution is all log k. Let me make this, and then the space is all 1. That's the solution, like the complexity analysis for the solution. Okay, let's move on to the implementation this time. Okay, so first thing first, we will create a mod, which is 10 to the power of 9, and then we're gonna use add function. Just basically calculate a plus b and mod the 10 to the power of 9. And also need the multiplication, that's the same thing, but we do it under the mod as well. And we could do subtract, same thing. And we're going to do the power, it's just a little bit more complicated, but we have discussed this before. So if it is 0, anything to the power of 0 is 1, so that's the base case. So otherwise, if it is an even number, so we're just going to reuse this x to the power of p divided by 2, and then multiply itself. So it's basically the same as x to the power of p. So otherwise, if it is an odd number, I will just do the x times x to the power of p minus 1. And that's it. That's how we can calculate the power function kind of in a logarithm time. And we also need this invert. So this invert is like a modular trick that whenever you do x to the power of the mod subtract by 2, it will basically give us the division. So this is like a theorem behind it. Maybe I will make a video on how to prove it, but just treat it as a truth that whenever you multiply something, inferred x is basically the same as divided by x if the log is a prime number. Okay, let's just move on. The sum is basically x times x plus 1 divided by 2. We're going to use this function later. Yeah, that's pretty much all. Let's go on with the function. So as we discussed before, we're going to need the sum between L and R to calculate. So we're just going to add this here first. And we also need to know the base. So base right now is 999, which 9 repeat for k times, but we want 1 repeat for k times. So what you're going to do is to divide by 9. So 999 divided by 9 will be 11111. And then the total answer is the base, and then multiply by the R sum, and then again we need to consider the mutation of the remaining k value, and each of them can have like R minus L plus 1 different variation, and finally we just return the answer. Yeah, that's pretty much all for the solution, and this all runs in O log k time because the most expensive operation is here, and for the space complexity will be O1. Yeah, that's pretty much all for the solution, and thank you so much for watching, and I'll see you next time. Bye.